class about residence time distribution analysis, which is important for different kinds of non-ideal reactor flow systems. Though we have all assumed till now that all reactors are perfectly mixed, particularly when you are talking about batch reactor or all those kind of things, or plug flow reactor, we are assuming it is a perfectly mixed reactor system and we are assuming an ideal behavior, but that is not really true. We'll see most of the time the reactor flow will not be ideal one, and we must know how to analyze, how to diagnose these kinds of reactor performance, how it is deviating from the ideal scenario. So the residence time of each of the molecule in the reactor is not same. So even if they are going together, for example in case of mixed flow reactor, those molecules which are going together at any moment, not necessarily they are staying in the reactor for same time period. So degree of the amount of time they are spending in the reactor is different. So each molecule degree of conversion is definitely going to be different altogether. For gas phase reaction, this is more prominent because gas phase reaction mostly occur in the gas liquid interface from the bubble. So it all depends on how much rate of reaction depends on what is the surface area of the bubble, and surface area of course depends on, in gas liquid phase reaction system, how much time it's spent in the reactor. So initially the bubble size may be very small, but finally the bubble size, as time goes, size increases. So it all depends on how much time they are spending in the reactor system. We'll be showing you here the gas liquid system for analysis. So more time it is spending, it is likely that interfacial area is more and maybe the conversion is different, but all the molecule which is coming together, all of them are not staying same time. So overall conversion will not depend on how much time on average each molecule is spending, but each molecule how much time is spending is more important for residence time distribution analysis. That we told earlier, the average residence time of bubble is not important, rather residence time of each bubble. So if I say there is 100 gas bubble is coming inside at any moment, out of the 100, each one, individual one, assumingly, anyway we cannot do individual molecule basis, but if we can do that each of the molecule how much time they are spending, so for each molecule how much conversion is happening, so if we sum them up all together, all the 100 molecules, that is a distribution rather. So that is called residence time distribution. Each molecule will not spend exactly same time, but their sum up if we do, we will find out what is the exact conversion is happening. So this is the purpose, this is the ideology for doing a residence time distribution analysis. Now we need to have some residence time distribution functions also in this class. So in an ideal plug flow reactor system, all the atoms of the molecule have been inside for same amount of time. So plug flow means we are discretizing the whole reactor into small segment, and it is continuously moving in a laminar fashion. So we assume there is no back mixing, but we also assume that in the axial mixing is possible. So that can also be sometime non-ideal. Similarly, in case of ideal batch reactor, all atoms has been inside for identical length of time. That is only theoretically possible, but we will see that is not really the true sense. It is not always correct. In all other reactor types, particularly the continuous tank reactor, which is actually continuous mode, the various atoms in the feed spend different time inside the reactor. We already told it, but it is not related to only plug flow or maybe batch. It is valid, nearly valid for all other reactors as well. So here we are showing the diagram how bypassing can happen in CSTR or mixed flow reactor. You see, when we are mixing, some of the molecule can very quickly from the entrance they can go out. So they are not really mixing. Some zones can be there which is dead zone, which is not at all being mixed. So those molecules will spend longer time. Maybe times can be infinity if it is really dead zone, no mixing is happening at all. And these molecules are spending maybe less than the average time spent by all other molecules, so it is not really perfect mixing scenario. And similarly, for example, here packed bed reactor, if the packing is not uniform, you can see some molecules are going very quickly in the void space, coming out so quickly, so maybe their interaction with the solid support or their conversion of those molecules is definitely lower, and those molecules which are spending longer time, they are coming out outcome may be something different, maybe degree of conversion is more. So actually we are observing here the whole picture, we are not going to analyze each and every of the uh, laminar molecule independently, not possible. So we are actually observing the overall picture here, and we also know here uniform picture of the molecule, maybe at uniform concentration. So residence time distribution of reactor is actually a characteristics of mixing that occurs in a chemical reactor. How the mixing is happening, how much it is ideal, from the ideal behavior, how much it is deviating. So those information is very much important for residence time distribution function. So distribution means we are having all the member of the whole population, and each molecule or how many molecules are spending how much of time, so it will give some. For example, we have known about normal distribution curve, so entire population, each one, for example 1 minute how many molecules spending, 5 minutes how many molecules spending, will have a complete distribution. We want to have it. Not all RTD are unique to a particular reactor type. Markedly different reactor can display identical RTD, so it is not necessarily that this is a feature of one particular variety of reactor. It can happen to any other reactor as well. Now RTD, how we are going to do those experiments is particularly determined experimentally by injecting one inert chemical molecule or atom that is called tracer. So in chemical reactor type we are injecting some of the molecule which can be located at the exit. So entrance we are putting some molecules which can be actually colorful compound or which can be determined more easily. These are called tracer at some time t equal to 0, and then measuring the tracer concentration in the effluent with different time frame. How is it going to change? In addition to being a non-reactive, easily detectable, the tracer should be also completely soluble. It should not adsorb to the wall of the reactor. So most of the time we can use colored or radioactive material along with some inert gas for most of the type of tracer. The tracer experiments is actually performed in two ways. One is pulse input. So an amount of tracer, for example N0, is suddenly injected in one shot in the running reactor inlet. So we are not giving it for a long time period. At an instantaneous moment we are putting some amount of tracer, and we are doing this job sorry, within a very small time frame, as short time as possible. We are going to inject those compounds in the reactor, and we will be measuring the concentration in the exit stream from the same reactor. So our time starts so when you are injecting, so possibly that is t equal to 0. This is pulse. So at a time everything. And the other variety is there, that is known as step tracer, where we are injecting for a little bit longer period of time and we are measuring the exit concentration also, but what we are adding in the inlet we are adding in a constant rate. So same amount per unit time, we are same concentration we are always giving at the inlet, and we are going to measure the outlet concentration. And what will happen during this run, after some time the concentration in the exit will become identical to the inlet concentration. So this is known as step tracer experiments. We can do it for time varying experiment scenario. So we'll discuss the derivation in next class.